Welcome to the lecture series of signal system. In the previous lecture, we have seen the basic concept of an LTI system. In this lecture, we will discuss the concept of convolution for the continuous time signals. So, convolution operation basically is a mathematical operation by which we can combine two signals to form a third signal. As we seen in the last lecture, what the convolution is. To convolution operation of two signals is defined as x1 convolution with x2 t, which is equal to minus infinite to plus infinite x1 tau x2 t minus tau. So mathematically it is combination of two signals x1 tau x1 t and x2 t to produce a third signal yt. So, and also what we have seen, if a system is given, suppose there is a system S, we are giving impulse as input to the system and it produces impulse response ht. If impulse response of the system is known, then we can find out output for any given general signal as input. So if xt is given as input in the same system, then output yt will be equal to xt convolution with ht. So if the impulse response of the system is known, then we can find out the output for any given input by convolving the input and impulse response of the signal. So here is another definition. The convolution relates input and impulse response of the system to the output, because output is the convolution of input signal and impulse response of the system. That's why we can say that the convolution relates input and impulse response of the system to the output. A signal xt can be expressed as continuous sum of impulse functions. Then an output yt can also be expressed as continuous sum of responses to various impulse components. What does this mean is, suppose a general signal xt is given to the system, what we stated earlier, that xt can be dissolved in components like delta t minus tau. In this form, xt can be dissolved in the components in the shifted form of impulse functions. Then output due to these impulses also can be written as summation of delta ht t minus tau and so on, all the components of the input signal. So what is written here, a signal xt can be expressed as a continuous sum of impulse functions. Then an output yt can be expressed as continuous sum of impulse responses to various impulse components. Next, if input of the signal is an impulse, then output of the system denoted by ht is called impulse response. This is what is known to us. So if input of the system is an impulse, then output ht is called impulse response, and ht can be written as it is transformation of delta t by the system. And any general signal xt can be expressed as we have seen in the previous lecture, it can be expressed as tau from minus infinite to plus infinite x of tau delta t minus tau d tau. This is what any general signal can be expressed in this form. And if the signal xt is given to the system, if this signal xt is given to the system, this system produces, if xt is given to the system, it produces output yt, and this yt is the transformation of signal xt, where this signal xt can be written as, integration from minus infinite to plus infinite x tau delta t minus tau d tau. So yt will be transformation of this given signal, tau from minus infinite to plus infinite x of tau delta t minus tau. Remember, then if yt is equal to transformation of the signal, this signal x tau del of t minus tau d tau, then x tau here is, it is the amplitude of the signal at instant t equal to tau. X tau is the amplitude, so it is a constant amplitude of the signal. We will put this constant outside of the integration. It will become x tau integration minus infinite to plus infinite transformation of delta t minus tau d tau. If transformation of delta t is ht, then transformation of delta t minus tau will be h of t minus tau. So in place of this delta t minus tau, we can put h of t minus tau, and this integration will become yt is equal to integration from minus infinite to plus infinite x tau h of t minus tau d tau. This is what we called it as convolution integration. This is what we called convolution integration. This relation is used to find out the output of a system if impulse response of the system is known. If and it is represented as yt, it is represented as yt is equal to xt convolution with ht. We can also write it as ht convolution with xt, because we seen earlier convolution property is commutative. So because convolution follows the law of commutation, we can write it as xt convolution with ht or ht convolution with xt also. Next, this integration convolution can be written, suppose xt and ht both are non-causal signals. If xt and ht both are non-causal signals, then definition for a causal signal is if signal exists only for the positive values of t, means x of t is equal to 0 when t is less than 0, then this signal is called a causal signal. A causal signal exists only for the positive values of t. For the negative values of t, the signal remains 0. And if signal exists only for the negative values of t, means if xt is 0 for t greater than 0, then this xt is called anti-causal signal. And if xt exists for both the region, for both the values of t, positive as well as negative, then this signal is called a non-causal signal. So in the given example here, xt and ht both are non-causal. It means that both signals will exist from minus infinite to plus infinite, means for both the regions of the time. That's why we will put limit here from minus infinite to plus infinite. So remember, if both the signals are non-causal signals, then limit of the integration will be from minus infinite to plus infinite. Next, suppose xt is non-causal and ht is a causal signal. xt is non-causal and ht is a causal signal. It means that when we will put these two in the integration, x of tau h of t minus tau d tau. Here xt will exist from minus infinite to plus infinite because it is a non-causal signal. Statement says that h of t minus tau is a causal signal. It means that h of t minus tau will exist only for this value greater than 0. When t minus tau will be greater than 0, it implies that tau is less than t. So it means that xt will exist from minus infinite to plus infinite, whereas ht minus tau will exist only for tau less than t. So there are two limits on tau. It is from minus infinite to plus infinite and it should be less than t. So the limit on the tau will be from minus infinite to t. In this case, we will put limit of integration from minus infinite to t. Again, if xt is causal, x tau is causal means if x tau is causal, then tau will exist only for tau will always be greater than 0 because x of tau is causal. For tau less than 0, this x tau will become 0. So tau will not take negative values. Tau will always be positive. And ht is non-causal. ht minus tau, it is non-causal. It means that tau can take any value from minus infinite to plus infinite. The one statement says tau will exist for the total period from minus infinite to plus infinite, whereas the next statement says tau will be greater than 0. So here tau will have two ranges. Tau is from 0 to infinite. Here tau is from minus infinite to plus infinite. When we will combine these two limits, we will find that tau will exist only for t greater than 0. So the limit of integration will be from 0 to infinite. This is in which case when xt is causal and h of t is a non-causal signal. Next, here if x of tau, if both are causal, then tau will be greater than 0 because x tau is a causal signal. Also h of t minus tau, it is also a causal signal. It implies that t minus tau will be greater than 0, which indicates that tau will be less than t. It means that limit on the tau here, this statement says that tau is greater than 0. This says that tau is less than t. If we combine both two limits, it will become tau is from 0 to t. So the limit of integration for if both the signals are causal signals, it will be from 0 to t. This is all for this lecture. In the next lecture we will discuss properties of convolution. Thank you.